Welcome to the segment on input output ports on the STM32F4. We will start with the diode clamp. Now, you would have read or you would have seen that the STM32F4 ports are 5 volt tolerant. So they say it is 5 volt tolerant, even though the controller operates on 3.3 volts, that is up to 3.3 volts. That means if you feed a voltage greater than 3.3 volts but lesser than 5 volts into the IO pins of the microcontroller, there is no chance of damaging the controller. Had there been no protection, feeding anything above 3.3 volt would have damaged the controller electronics. So these pins are tolerant. So the tolerance of the pins come from this particular circuit that is called the diode clamp. Now, I'm sure you are aware of how a diode operates. A diode is an electronic device which can only conduct current in one direction, and it blocks current in the other direction. So that's what a diode is. Now, say you have a voltage V in which is going into the pin. So if this is the controller and these are your pins, this is the internal diagram of electrical diagram of one of those pins. So every pin will have a diode clamp like this. So what happens is there are some few scenarios. That is, first scenario is where we are actually feeding a lower voltage than the cutoff voltage. For example, so say VDD-FT is 3.3 volts. So here we are holding a value of 3.3 volt, and we call it stiff because even if we load this particular circuit, this voltage is not going to droop. It is going to stay almost 3.3 volts. So this, and VSS is also stiff. So these are stiff voltages. Okay. And say suppose you have you provide a voltage which is lesser than VDD-FT. Okay. So this is a voltage that is maintained here, and so it's anyway lesser than VDD-FT. When the voltage is lesser here, of course, the diode is reverse biased because the voltage here is higher than here. So the diode is reverse biased, and this diode is also reverse biased. So both the diodes are inactive when you are feeding a proper voltage below, say, 3.3 volt. And this is one scenario. That is a normal operating scenario. Now, if there is a case where your Vin is greater than, say, your tolerance limit, that is, say, 3.3 volts, not tolerance limit, rather the operational limit that the processor has, and suppose you feed in, say, 4 volts here, this is the voltage that keeps track of that. And basically what happens is, so the drop for the diode, that is the forward conducting bias of the diode, is 0.7 volts, as you know. So if the voltage is VDD-FT plus 0.7 volts, okay, so 3.34 volts is say it's plus 0.7 volts. So basically what the protection diode does is it creates a path for that excess current to flow out through the VDD-FT diode. So this becomes forward biased, and this current flows out through here. So diode 1 is on, diode 2 is off, and Vin is around VDD-FT, and this is a stiff voltage. So that is the purpose of the protection diode 1. Now if the voltage goes below, like it goes below minus 7 volt minus VSS. So whatever the VSS voltage is, say you are now feeding an extremely low voltage. Now that actually turns on this diode and the current flows through here, and thus the excess current flows through here and the circuit is still protected. So that is the use of the protection diode clamp. So even though the arrow that is drawn is in this direction, it actually should be this way. That is because this current flows from this direction to this direction. But nevertheless, know that this again a very low voltage is compensated from here to here. Okay, so this diode is on, this diode is off, but then a very low voltage protection is provided by this diode as excess voltage, excessively low voltage is compensated here. So this is how a protection diode clamp works for the IO pins in this controller. So lots of controllers will have this protection circuit, because of which, so these are three cases of the same, this is the same pin, but these are three scenarios where one's V in is normal, it's less, here it's greater than this one, here it is lesser than this value. The circuit is, but don't try to give very high voltages above 5 volts will again damage the circuit. So do not give any voltage above, so 5 volts. So if you are subjecting the pins to some TTL levels which are 5 volts, so you are safe. So don't worry about connecting 5 volts to any of the IO pins of this of the STM32 Discovery board. But nevertheless, if you can connect lower voltages, that is somewhere around 3.3 volts, that will ensure greater safety. So this is how your protection diode clamp works. Moving on, there is another electronic circuit called the Schmitt trigger, which is used in the IO port. Now, a Schmitt trigger device, okay, it is typically used in signal conditioning applications to remove noise from signals used in digital circuits, particularly mechanical contact bounce in switches. So when you have a mechanical switch, so you have a mechanical switch, push button switch, and this is a connection. When you close the switch, there is a ringing, there's an initial oscillation, after which the signal steadies actually. Okay, so this is called switch bouncing. So the moment you any switch for that matter, it will oscillate for some time and then the signal will go steady. Now, in such a scenario, if the signal is fluctuating when you are applying an input, say to this circuits, the microcontroller will remain undecided as to what voltage level is being fed to it. So you have an IO pin and there is a switch here, and you close the switch and you have some oscillations to begin with. Okay, so this might affect the reading of the microcontroller. You want it to be 1, but it will fluctuate between 0, 1, 0, 1 for some time, okay, before it steadies. Now, Schmitt trigger is a device which doesn't prevent the bounce, but it is clever enough to filter out the right signal from here if there is a bounce. So Schmitt trigger is an active circuit which converts an analog input signal to a digital output signal. So coming to the diagram here, so normally when there is an input signal going into the pin, as you can see, the waveform is going to fluctuate in the beginning. And what will happen is, if the Schmidt trigger was not present here, and if this was the point on the waveform where the input would be considered to be high, if there is a fluctuation like this, whenever it crosses this point in the positive or the negative direction, so if this point is taken to be the power on point, or this point is taken to be the logic 1 point, so every time it crosses here, it becomes a 1, but then when it comes down it becomes a 0, then it becomes a 1 0 1 0, okay, and then probably from here it becomes a 1 because the signal doesn't fall below the red line. So there is a fluctuation before the input is registered as continuous once. So this is completely undesired behavior. We don't want it to happen this way. So what the Schmidt trigger does is, when such a waveform comes in, the switching on point, that is is higher than what we saw previously. So maybe it will switch on at a higher voltage, close to 3.3 volt. Okay, that is where the switch on is going to happen. But the switch off, that is the signal turns off at a different level. Say this is 0.2 volts. Okay, so the turn off voltage and the turn on voltage are at different levels. Now if there is an oscillation, if the signal goes high and it oscillates like this, it doesn't come down to the level of where where the turn off is. So let's assume that there's a signal which is fluctuating, but it doesn't come as low as the turn on. So the waveform slowly, the amplitudes slowly diminish like this. Then we immediately see that it protects against fluctuation. So here you see there are two on states which is protected against. So our desired waveform looks more clean here. Now this particular difference between the switch off and the switch on, this difference, the distance between these two lines, is called the hysteresis. And you would be seeing a lot of hysteresis curves, and the Schmidt trigger is actually denoted by a hysteresis sign only. So this means the Schmidt trigger basically, and the Schmidt trigger will provide you that hysteresis, so that your input waves are input is much cleaner than if you did not have a Schmidt trigger. So the input changes. So the circuit is named a trigger because the output retains its value until the input changes sufficiently to trigger a change. So if there is a fluctuation, it will hold the input value. In the non-inverting configuration, when the input is higher than a chosen threshold, the output is high. When the input is below a different lower chosen threshold, the output is low. And when the input is between two levels, the output retains its value. This dual threshold action is called hysteresis and implies that the Schmidt trigger possesses memory. That is, within this it holds the value. Okay, so if it fluctuates within these two lines, suppose it's powered on and it fluctuates within these two lines, it holds the value. So in a way, Schmidt trigger has memory. And Schmidt trigger is also an integral part of an input circuitry in a microcontroller. Even out the disturbances that come into the input pins. Okay, so and one of the disturbances is the switch bounce that we spoke of. Moving forward, we have different pin states that the different pin states that the microcontroller's pin can have. One pin state is called high impedance. A high impedance pin is characterized by having a high impedance which effectively limits the change in current flow from the electrical circuit it is connected to with respect to a much larger change in input voltage. It is floating unless another external device or circuitry, pull up or pull down, is driving it. Input pins are open collector pins, and open collector pins are high impedance. Okay. So, suppose you configure a pin as input. Suppose this is the microcontroller controller and this is the input pin. Input. So we have configured it as input. Okay. High impedance would mean that suppose you do a change in voltage here. Okay. When you do a lot of change in voltage, the current, whatever current is you have in here, is almost constant. The current does not change. Okay. So if there is a change in input voltage, there is no change in current. And it is so we'll talk about what a floating pin is. So it is like a floating pin until there is some external circuitry controlling it. So input pins are open collector pins and are high impedance. Okay. So an input pin is a high impedance pin. In other words, impedance itself means that so if you have V equal to current into resistance, okay, resistance equal to voltage over current. Okay. Now, impedance is also can be also written as delta V over delta I. So delta V by delta I is a change in the value of voltage to change in the value of current. Okay. So how do you, so when you say you have a high, so if it's impedance, then let's not call it R, let's call it Z. So Z in is say input impedance. So delta V by delta I, when the value has to be, if this value is large, means delta I has to be small and delta V has to be, it has to be small and delta V has to be pretty large. Okay. So thus we can get higher input impedance. That is, there is a resistance in the input. And this is what is mentioned here. That is, there's a higher change in voltage amounts to a low change in current. Thus, the input impedance is high. That is what it means here. Low impedance means a pin that can source or sink current. So, the high impedance pin that we saw does not source or sink much current. So that pin is almost inert. A low impedance pin is a pin that can source or sink current. A floating pin is if a pin is called floating if it's left unconnected and is not driven by a pull up or a pull down. Its voltage level is undefined and unpredictable. So when a pin is floating, suppose there is you have a pin and it is not connected and it does not also have a pull up or a pull down, it is called a floating pin. And we should not keep floating pins in our application. Pins should at least have a pull up or a pull down, and it should have a definite value. So a pull up or a pull down are resistors basically, and these resistors are used to set a specific level, logic 0 or logic 1 at a floating pin. A pull up resistor is connected to the power supply so that it can pull the floating pin to a logic high level. A pull down resistor connects the floating pin to the ground level. So if you have a pin, so there is an internal circuitry also, which is a weak pull up and weak pull down that the microcontroller has. So R1, R2, and if you enable the weak pull up, this pin is set to a initial voltage. So you're tying the pin to an initial voltage, or if you have a weak pull down, you're tying it to a 0 volt. So this pin is called a pull up or pull down if you connect it to a voltage source through a resistor, of course, or you connect it pull down if you connect it to the ground through a resistor. So this is called pull up or pull down. Short circuits on digital pins or attempting to run high current devices from them can damage or destroy the output transistors in the pin or damage the entire SoC. So be careful. Short circuits on digital pins or attempting to run high current devices from them can. So do not try to drive devices which need a lot of current here. So you can maybe drive an LED, but don't try to drive something which needs high current. That's an absolute no. There has to be driver circuitry in the middle, and the controller should just be used to switch on the driver circuitry, which will in turn allow higher current to pass through them. But the controller must not be used to source or sink high current. Like I said, an LED, glowing an LED is fine, but more than that, a controller is incapable of driving anything higher than that. Now coming to a push-pull circuit. Now all the circuits that we are discussing here are a part of the IO, are a part of one IO circuitry, and later on we'll see all these circuits come together. So a MOS push-pull circuit comprises of a PMOS and an NMOS transistor. Now till before this we had talked about the different pin states. So when we come to these circuits, we will also talk about the pin states, which will help you understand these IO circuits better. So this is a MOS push-pull circuit, and it's called push-pull because at any point in time one of these transistors are on and the other is off. And when you are talking about an IO, it's essentially about switching between positive or switching between 1 and a 0. So it's switching between 1 and a 0, and quicker the switch between 1 and a 0, say it's 3.3 volts to 0 volts, quicker the transition, okay, better the IO. So you wouldn't want the transition to happen over a long period of time. That is, you from 0 you provide the high volt, and then you see that the input is not immediately going high, but it's following a ramp of this sort, which is not good. So the transition here should be a steep curve. When there's a transition between these two transistors, switch between these two transistors, when one switch is on and one switch is off, so it provides a much faster transition. Now this type of configuration is suitable for unidirectional lines. For example, you have SPI UART where one device is connected to the line. So you have UART protocol here. So if you have a pin here and you can connect it to the TTL, maybe a converter from where you connect to your computer using USB. So you can use this, say you are communicating with your desktop, so you can directly connect the TTL to this pin, and in that case this will be driven by a push-pull circuit. Or you could have a SPI communicating with some other peripheral on the board, like it communicates with some accelerometer or something, okay, so maybe through SPI. So for such communication where you have only one device on the line, this kind of a push-pull configuration makes sense. So going forward, we now see how the push-pull works. So if there's an internal signal here which operates the push-pull. So if this is low, the PMOS is powered on and the VDD appears on the output pin, something like VDD shorted to output. So a state is a 1. Okay, so you have the VDD flowing from here to here. Okay, now the output needs to have a resistor here. to limit the current to the specified value that the pin can safely supply, because this is almost shorting the VDD to the output. So when the internal signal is low, you have the voltage flowing out like this. Now, since and so if a current is flowing out freely from VDD to the output pin, this is low impedance. So you understand what low impedance is now. That is, this one is you have a current that is flowing freely, and in fact you can short it. If you do not put a resistor of a proper value, you can overdraw from here and you can damage the circuit, like it says here. So this is low impedance again. So when the internal signal is low, this is the state where current flows from VDD to the output pin. Now this is an output. Okay, so in the next scenario we will see when the internal signal is high. When the internal signal is high, this PMOS goes off and this one goes on. So and like we said, the transition time between these two is very fast, and at that time current flows from outside to the ground. It goes like this. So if the input is high, NMOS is powered up, and so the output pin is grounded, something like ground shorted to output, so that it's like a state 0. Okay, so this is like 0, so output pin is at 0 now. Previously we saw that the output pin was at 1 because the current was flowing out. Now the current is flowing in. Even here it is a low impedance. Because there's a flow of current. So as we can see from here, output does not always mean that the current will flow out of the pin. Okay. It does not mean that the current will flow out of the pin. So it's not always that for an output pin, sometimes we think that something is going to always flow out of the output pin. That's not the case. It can be this way also. So that's how the push-pull works. Now the push-pull is a configuration where you see that there is low impedance in both cases. That is when the PMOS is on and the NMOS is off, and vice versa. So there is another type of output which is called the open drain. Now open drain is different from push-pull. Now open drain configuration is only capable of driving a line to the ground. So there is nothing supplied from the controller as such. This is something like a switch. So if you connect something on this line, some external chips on this line, say communicating with over I2C chips for certain functionality, and then if you connect it to the output line, the only job the open drain does is to short the circuit from here to here. That's all that the open drain is capable of. Now, since this is the only way the open drain can function, if we have to have lines with logic levels, okay, what we need to do is we need to connect this open drain line to an external voltage source, say VCC or something. Okay, so the line, if this is not connected, the line is going to be anyway held high at say 5 volts or whatever, and then when this internal signal is on, a current flows through and drives this to 0 volts. That is what an open drain can do. And the usefulness is, if you have multiple, so for push-pull we saw that we can only have a 1-to-1 correspondence for UART, SPI and so on. For open drain we can have multiple devices connected. Now the downside of open drain is the switching time is higher. Push pull, the switching time is fast, but for open drain the switching time is higher. That is, from off to on, there's a ramp basically. So the changes will not immediately take effect over the line. It takes some time. So this is an explanation of how the open drain works. When this is high, the NMOS turns on and it shorts the output to the ground. That's what we saw. Now, and when it is off, so when the internal signal is low, the NMOS stops conducting, thereby disconnecting the output from the ground. If no pull-up resistors are connected to the output, the pin becomes a floating one. So like we saw, it's a floating pin. The output is undefined, so which is not good. Okay, so, and if when the signal is high and it conducts again, it is a low impedance. It is low impedance again. Okay. So that's what an open drain pin is. So we can configure the pins for open drain, push pull, and so on. So we'll see all that. Now we come to the internal pull up pull down that this controller has. This pull up pull down that you see are internal to the controller. So suppose you have an open drain pin, sometimes you may get away with having a weak pull up. So these are weak pull ups, these are not strong pull ups. So for example, so this STM32 F411XC they have inbuilt weak pull up and pull down resistors which are configurable. So weak pull up means these resistors are of high value. High value means, so when we say it's a weak pull up, the weakness comes from the limited amount of current that it can supply. So when we say it's a weak pull up, weak here means low current. Okay, so weak means low current in this case. So weak or high resistance pull up pull down resistor is good because it will not require much current from the driving circuitry to work against the resistor. Batteries will thus last longer, parts can be smaller and don't get as hot. So if you have a weak pull up, basically if you're holding a line at say 3.3 volt and you are passing that value through a high resistance, generally what happens is you consume less current. If you consume less current, if this is a battery operated embedded system, obviously less current would mean less battery drain. Okay, and obviously the parts will not get hot because the current flow is going to be limited. A strong or low resistance pull up pull down resistor is preferred when the time constant formed by the load capacitance of an input gate capacitance and the PCB trace capacitance is small. So rise fall times will be short. So the downside of a weak pull up is because the resistance is very high, you have something called as the RC time constant, which is going to be high. So basically when you feed in when you are actually making any changes to these lines, there is going to be a delay between the transition from say 0 volt to 3.3 volt. Okay, now that is for a weak pull up. So that is a disadvantage of a weak pull up. A strong or low resistance pull up is preferred when the time constant formed by the load capacitance, often the input gate capacitance, and the PCB trace capacitance is small. So rise fall times will be short. Noise currents from unintended coupling and EMI will result in smaller noise voltages. Okay, so if you want the transition to be faster, then you have to reduce the resistance value, but the downside is it will draw more current. So there is always a trade-off here. And because for a strong pull-up, it will result in smaller noise voltages. Now we'll just go through the pull-up pull-down functionality. So we have, if the upper base of this particular pull-up is made high, so a weak pull-up is activated. These pull-ups can be used for both inputs and open drain configurations. Now this one you can use for an input pin, and you can also use it for an open drain configuration. And if you make this low, then a pull-up is activated. On the other hand, if you make this high and this low, then pull down is activated. It can be used again for both inputs and open drain configurations. There are rare cases when both pull up and pull downs are simultaneously activated. There are cases, but they are rare. So we don't do that generally. This is a pull down configuration, and pull up and pull down are generally for, we've seen it's for open drain, because open drain doesn't source any current, it just shorts to the ground. So if you have a pull up or a pull down, that decides the open drain behavior. Okay, and you can add a pull up and pull down to input also. For example, if you make an input active high, suppose, okay, so it's an input pin. If you want to keep it as active high, then you need to internally you have to activate the pull up to the input, so it's high, and then you ground it from outside, and then it becomes low. Show that in case you are wondering what I'm talking about. So you have, say, an input pin. Now this is an input pin, and input pin is high impedance, as we know, because it's getting fed into that Schmidt trigger. Okay, now we feed some voltage value here, and since it's high impedance, what we'll do is we'll have a weak pull up to this input pin, and we generally do this because otherwise this pin is high impedance input pin. If we don't apply a voltage to this pin is going to be floating, which we do not want. So either we could supply internally, or there could be an input pin could also have an external pull up. So in this case, we are considering a scenario where we enable the pull up here, and the internal, and this is an input. So this is, say, 5 volts, and when we ground this, short this to the ground, this becomes 0 volts. Okay. On the other hand, if we have a weak pull down, that is, we activate this for an input pin, default is 0 volt, and then we can connect it to, say, VCC or 3.3 volt, and this value goes high. So default is ground, and this goes high. So this is one use of the pull up, and another use of the pull up is, of course, the open drain circuit that we saw a while ago. So this is your pull up and pull down. Putting it all together, now we have this is how one in IO pin circuitry looks like. So everything comes together here. We studied about the diode protection circuit. We just saw the pull up and pull down. We saw the push pull or open drain circuitry, and we saw the input circuitry. So all of them coming together, and we studied these individually. Now we will see the effect that they have when they are put together. So let us briefly go through this diagram. We have the input coming in here, and it goes to the input here, that is to the Schmidt trigger that we saw previously, and the output also flows out through here, as you can see, and this is the analog input. So this comes in through the IO pin only, but it is shown here separately. So this is the analog. So this pin can be a digital or an analog input output, right? We have not been speaking about analog. So if it's analog, then this whole thing is bypassed. So that's another scenario which we have not talked much about. But nevertheless, so this is the output driver section. This is the input driver section. So the input driver, as you can see, a value goes straight to the analog here. So this is an on chip, maybe some peripheral, for example, analog to digital converter or something. So this is the path. This is the path to alternate function input. So alternate function input would mean, besides just being IOs, these pins are also for alternate functions. For example, if you enable this pin for, say, SPI. So SPI is an alternate function. Serial peripheral interface will be an alternate function for this particular pin, and then the path is going to be this for input. Otherwise, if it's just input output, then it will flow through here. That is, it's an input output data register. So 3 functions here. Similarly, in output also it is going to be the same. This is write and output data register. So this is plain output, and this is alternate function output. So there's a multiplexer. You can just configure this accordingly, and output control will output the values accordingly. So when you have an output like this, so same SPI, when it has to output something, it is going to take this path. This is going to be inactive that time. So it's going to be taken over by the SPI when we set up the alternate function, and we set up, so every pin will have a field of a few bits defined where you can decide which alternate function this pin is going to have. So if you want it to work as a UART, or if you want it to work as a SPI, all of that is going to be decided by these fields, bit fields. Okay? That's the alternate function bit fields. So this is in short what the IO circuitry is. Now we will go through different configurations that we spoke of now. So we'll go through different configurations of the IO circuitry and see how they look. And of course, all ports have external interrupt capability. To use an external interrupt line, the port must be configured as in input mode. So of course, this input data register input port that you see here, okay, it can also be used as an interrupt. So you have to configure the port as an input port, and then any input will trigger an interrupt.